So here's an example problem. We have a composite wall consists of 3 materials, and there's one-dimensional steady state heat transfer through the materials from the hot fluid, which is at 120 C over here, this is T infinity, to the cold surface, 24 degrees C on this outside. Maybe this is the inside, designated with an I subscript, and the O is outside. And the question is determine the temperature of the surface on the inside. Find this temperature right here. Well, the way to there's a number of ways to set this up and solve it, but let's do it with resistors. So we would put a node for each clearly identified temperature. So here is TSO. That we know the value of, it's 24 degrees C. Here is T infinity, we know the value of that one, 120 C. We're looking for TSI, that surface temperature, and that's really a node. Okay, now I don't know this temperature, T1 or T2, and I don't even need to maybe name it, but we could name it, and so we call it T1 and T2, some interface temperature between material A, B, and between B, C. Now, I failed to point out a lot of information's given about the thermal conductivity and thickness, the thermal conductivity and thickness, thermal conductivity and thickness of each of those slabs. Okay, so we're going to have flow Q through this network, and it's made up of resistors. And those resistors are 3 conduction resistors, L over Ka, plain wall. This is for material A, L over Ka for material in slab B, L over Ka material slab C. And we have 1 convection resistor, 1 over HA. Now at this point, you can say, well, the area is not specified. And so let's work everything per unit area squared. Or, this is my preferred way, or I recommend to students this way, is to go ahead and pick the area be 1 meter squared. It's like everything will have either per unit meter squared in it, or you just solve by assuming 1 meter squared for the area, cross-sectional area. Because isn't this area the same as this area, that area, and that area? Aren't they all the same? Yeah, they're all the same areas. So pick 1 meter squared, and then you're going to solve for that temperature, TSI. All right. So we can put in, let's see, at this point, how would you recommend to solve for TSI? This is our unknown right here. Anybody want to suggest a way? You know this one. This is 24 degrees C. You know T infinity, that's 120 degrees C. Do you know enough information to calculate each of these resistors now that we picked area to be 1 meter squared? Do you know the H? Yeah. Do you know the L and the K and the L and the K and the L and the K for each of those materials? Yeah. Do you see the recommended strategy then? Go ahead and compute all those resistors, sum them up because they're all in series to get an equivalent resistance, and then solve for the Q. This is kind of like first find Q, and then I could focus on only that convection resistor to find TSI. So, yes, sir? Absolutely. Yeah, you can do that too. But you have to do things correctly. That's all I ask on exams. So you'll stay symbolically a little longer. Yes?
So you're saying the way we solve for that missing convection is to add up the resistance of A, B, and C? We do L, K for each of them?
Yeah, let me go ahead and do that. So what we're going to do is we're going to have this, the resistance equivalent for the whole system is 1 over HA plus L over Ka for material A, plus L over Ka material B, plus L over Ka material C. That'll give me a number, and won't it be in units degree C per watt? Will that have units degree C per watt? Then we say, look, we're going to have the flow through the whole network is equal to what drives it, T infinity minus TSO. That's the large delta T over the entire network, divided by this R equivalent. That allows me to calculate Q. All right. Once I calculate Q, then I focus only on that first resistor, and I say, you know what? Q is equal to, you could put it a number of ways, but let's put it T infinity minus TSI. Finally, an equation where my unknown of interest is TSI, divided by that R convection, which is 1 over HA, or just forget about that. Just put up the HA times to T infinity minus TSI. Okay, so I can use this equation to get TSI is equal to T infinity minus Q divided by HA. Or if you wanted to, you could write it as T infinity minus Q times R convection. And now somebody says, well, calculating Q is an intermediate step. Why can't I just bring this part up? And then you'll say, okay, so that's T infinity minus TSO, R of the convection divided by R of all of them, the equivalent network of series. And then you'll see, oh, that's the fraction. That's the fraction of the resistance due to the convection. So, does that all make sense, how to solve that one? Let's go ahead. I think I have it worked out on the next slide. So, I calculate the resistors. I get a total R. Notice the units, degree C per watt. I backtrack and I say, well, what is that fraction of resistance due to the convection? What's the fraction due to the conduction through slab A? What's the fraction of the resistance due to the conduction through slab B? And the fraction due to conduction through slab C? And I see that the vast majority of the resistance to heat transfer is due to convection. 83% is due to convection. Anyway, I calculate that Q, 2000. I come in here and I calculate the TSI is 40 degrees C. So it drops from 120 to 40 degrees C, and then drops the rest of the way to 24 degrees C as you move through. Look good? All right. Well, you take the same type of problem and maybe you just change up what's given and what's you're asked to calculate. So in this case, it looks like the same problem, but they've taken away the thermal conductivity of material B, and they've given you TSI, and now just solve for the unknown KB. What's the thermal conductivity of material B? So since we're familiar with the problem, I think it's helpful to set up a resistor network where you have the nodes, making sure that they're temperature nodes, and then you have these resistances. This is resistance slab A, resistance slab B due conduction, resistance slab C, resistance on the convection, and what we have is a flow, Q through the system. I would go ahead and pick in your equations, area is equal to 1 meter squared. So if I go back and I look at these equations here, I always had 1 meter squared, 1 meter squared, 1 meter squared, 1 meter squared. The area was always just 1 meter squared. Same thing is my recommendation for here. Now, the strategy would be, I know this temperature, that's 120 degrees C. I know this temperature, 90 degrees C. I can use those two temperatures plus the resistance in the convection to calculate what? Q. So what would Q be? It would be TS, or T infinity minus TSI, divided by 1 over, divided by the resistance, or 1 over HA, or just forget about the resistance. Sometimes you just put an HA there. And so you have that flow. Once I know that flow, that same flow goes through here. And so I can focus on calculating T1. And then I can say, okay, well, the Q through slab A is K material A, the area of 1 meter squared, divided by the thickness of material A, times that TSI, which is 90 degrees, minus T1. I can calculate T1. So it's like, okay, calculate Q, then calculate T1. Then focus on this resistor in order to calculate T2. Okay, so then Q is equal to K of C, A divided by L sub C, T, this is TSO, T2 minus TSO. Let me pause. Is this equation correct as written? Thumbs up if you like it. Look good? You follow along? So now we solve for T2. All right. You can solve for T2. Then we focus on the slab B. So this equation was focusing on slab A. This equation was slab C. Now focus on slab B. And what you have is the same Q is equal to the KB A divided by L sub B, T1 minus T2. And finally, KB is equal to Q, L sub B, divided by A, T1 minus T2. I know that you could maybe skip calculating T1 and T2. It's just equations get a little long and maybe a little more error prone. I think if you do these, you'll find you can stop and pause and say, does that number look reasonable? Does T1 look reasonable? And if it doesn't look reasonable, let's say it's below 20 or above 90, then you got a problem. Look for your error. Look for a sign error. Okay. Same thing with T2. All right, so then let me go to the solution that's worked out on the next slide for this problem. And there it is. And so 0.465 watts per meter degree C. These problems are just made up. You just change some numbers and then good for the next homework set, or good for the next exam, or good for the next lecture. Okay. So in summary, we use this L over Ka for conductive resistance through a plane wall. When you have a cylinder, as you get more and more familiar, you'll remember natural log R2 over R1 divided by 2 pi KL, as well as for a sphere. This is less common, cylinder, layer of insulation around a pipe, that's more common. But this one is also available in your equation sheet and worked out in the textbook and worked out last time. Let's solve a cylindrical problem. So we have a hot water flows through a 3 centimeter diameter thin-walled copper pipe that is wrapped with 2 centimeters of insulation that has a conductivity of 0.05 watts per meter degree C. There's a lot to digest in that first sentence. So maybe think about, this is the center of that pipe. We're going to think about radial dimension. We're going to go out to R1, right? And then there's a couple key words in here. We know that the water flows through that copper pipe. Okay. What is R1 that gives us that cross-sectional flow area for the water flow? What is R1? 0.015 meter. 1.5 centimeters, true? Okay. You could then calculate A1, which is pi R1 squared. Or if you want to do pi D1 squared over 4, either way. Okay, that's that cross-sectional area for water flow. Now, there's a key word, thin-walled pipe. What is the outer thickness in R of that copper pipe? If it's thin-walled, it's negligible. It's the same as R1. right? That's the key concept of that. Then they wrap 2 centimeters of insulation. So what is R2? The outer, the radius of the outer layer of that insulation. The insulation goes from R1 to R2, and they say that it's 2 centimeters of insulation. So here's the question. This was, maybe I should put 1.5 centimeters, right? So R2, first clicker question of the day. Is that going to be, 3.5 centimeters or 5.5 centimeters? Answer A or B, or other, answer C. So let's go ahead and stop, everybody, and I hope. Let's stop. Let's do this. Let's try and draw it like this. This is the pipe. There's the center line. What did we say that diameter was for that thin-walled copper tube pipe, whatever? It's 3 centimeters, right? Now, if somebody's going to sell you some insulation, they're going to wrap it around. The insulation will be like this. Okay, this is the outer diameter of that insulation. Now, this distance right here, what would you call that distance? Would you call that the thickness of the insulation? Yeah, okay. In the problem statement, what is the thickness of the insulation? 2 centimeters. All right, somebody tell me what is this diameter. Let me label this one D1 and D2. Somebody tell me, let's change it from multiple choice numeric. Perfect, numeric. You type in D2 in units of centimeters. Numeric. What is D2? All right, let's go ahead and stop this show. So now let's go ahead and show the results. And so a lot of us said, hey, it's 7 centimeters. Some said 5, some 6.5, 0.7, 3, 3.5. All right. Well, okay, it's 2 centimeters and 3 centimeters. So if you just went this way, it would be 2 plus 3 plus 2. Isn't it 7? 7 centimeters is the correct response. Now, before I go and grade this, I want to go back and I want to ask this question again. R2. R2, what is it? Is it 3.5 centimeters, 5.5 centimeters, other? So what is it? Numeric response? No, not numeric. Stop that. What did I just do? I want to go back to the same multiple choice, right? So now we go back to this question. What is R2? Is it A, B, or C? All right, everybody in? Let's go ahead and stop. So what do we have? So yeah, I mean, if the diameter 2 is 7 centimeters, it's 3.5 centimeters, isn't it? All right. I don't know what the 1 is doing. Maybe they were still trying to respond. But let's go back. And so we're improving. Now, if you're part of the 58%, great. If you're part of the 37 or 5%, please, it makes it more difficult to grade your exams. Because I'm trying to figure out what you did. And you don't want a trivial error on the radius, do you? So if you need to clear that up in your mind, please do so, okay? Because somewhere in this semester, either the first exam, second exam, or third exam will be a pipe. There's so many pipes in heat exchangers and in heat transfer with some insulation or layers or radius or thicknesses that we have to be careful there, okay? All right, so now we have that R2 2 is clear in our mind. Let's continue to read. The water that flows inside is 80 degrees C with a convection coefficient 3,500 watts per meter squared degrees C within the pipe. The surrounding air is at 25 C with a convection coefficient of 20 watts per meter squared degrees C. Calculate the rate of heat transfer per unit length of the pipe. So it's the hot water is going to be transferring to the cooler air. That's the direction of our heat transfer. And we're interested in calculating this Q. I'm going to say it Q prime. It's how many watts per unit length of the pipe. The length of the pipe is shown into the paper, into the board. All right, maybe I can turn it sideways, and then it would be like this is the pipe with its insulation, and that's the length, right? Now, what I could do, and this is just like picking an area of 1 meter squared, I could pick a length of 1 meter and do the calculation, and then remember, oh yeah, I picked it per 1 meter, so then I express my final answer in the correct units. All right, so I'm going to pick this L is 1 meter length. Okay, so we have a convection resistance, get from the fluid on the inside to the surface on the inside, to the surface on the outside, to the fluid on the outside. Now I did that pretty fast, didn't I? And maybe it'll take you a little longer, but you have really 4 temperatures. Okay, what is this temperature right here in my network? That's my 80 degrees C. What is this temperature in my network? 25 degrees C. Very good. Now, you don't know the numeric value of TSI and TSO, but what is, in words, what is TSI? It's the temperature of my copper, thin-walled pipe. What is TSO? The outside insulation, the surface of that insulation on the outside. Okay, so we're going to have resistors that go from here to there. So this is a 1 over HA. Now, this A is the area on the inside. Do you know what the area on the inside is, or area 1? I call it right here area 1, right? Let's stay with 1. Area 1, I just did it, but hold it. This is the flow cross-sectional area. This would be 2 pi R1L. Is that right? It's the circumference times the depth. So it's the length of this line, that's their circumference, times the length. Doesn't that give me the area? Is this correct? 2 pi R1L. Yeah. And then this area over here on the outside will be, area 2 would be 2 pi R2L, and we just worked really hard to get the R1 and R2 squared away in our minds. All right. So then this is going to be H on the outside. This is H on the inside, A2 or A outside, either one. Now, what about this resistance conduction through the layer of insulation? You have to remember maybe the equation. You go look it up. Natural log R2 over R1 divided by 2 pi K L. So you would plug in your numeric values for the H's and the areas, and this will give you a resistance. That'll give you resistance. They're all in series. You can sum them up. So you get this R equivalent by summing those 3 resistors. And then if you wanted to calculate Q, it would be the delta T, T infinity on the inside minus T infinity on the outside, divided by that R equivalent.
For the middle resistor?
Yeah, that middle resistor is this equation right here. Yeah, this is where I used that equation. So this is through a cylindrical wall, one-dimensional steady-state heat loss. All right, so now I need to finish off this problem. So what we have is, for this first resistor, we have 1 over 3500 watts per meter squared degree C times pi times either 2 radius or 1 diameter, 0.03 times our length of 1. And then for this middle resistor, we have the natural log. You either can put the ratio of the diameters or the ratio of the radius. Either way, it works. Divided by 2 pi k. K is 0.05 watts per meter degree C times 1 meter length for length L. And then on the outside, last resistor, 1/20 times pi times 0.07 for the diameter times 1. And so this works out to give us 0.003032 degrees C per watt, plus the middle resistor, 2.697033 degrees C per watt, plus 0.22736, giving a total of 2.9274 degrees C per watt, of which we can go back and see that this is 92.1% of that resistance, and this resistor on the outside, convection, 7.8%, and this is 0.1% negligible. So scroll down a little bit and we'll finish out this problem. The Q is equal to the 80 minus 25 divided by the total resistance, 2.9274 degrees C per watt. This were difference in degrees C, so Q comes in at 18.8 watts. Now we wanted Q prime, which is Q divided by L, so our Q is 18.8 watts, and we picked length to be 1 meter, so Q prime is 18.8 watts per meter. And that finishes out this problem.